Okay, we're trying to work out which one is going to be the major product, which isomer, so if Z or E alkene, for the elimination of haloalkanes. First of all, the general mechanism: a base takes the hydrogen gives the electron to the p orbitals of the two carbons to form the double bond, and then the bromine leaves. So in all cases, we will have HBr as the side product. But we have two different options, because as you can see, we have quite a complex molecule. So the position of, so here I think you need to picture the fact that we won't have this bromine anymore and the hydrogen anymore, but we have a double bond. Yeah. And around this double bond, we have different groups. We have a CH3 and a C2H5. And we know that if we have different groups around the double bond, their position matters, because it gives a different isomers because of the restricted rotation around the double bond. But we need to be able to work out which one will be the major and which one will be the minor product. And we need to do that by using those two diagrams here. They're called the Newman projections. And it takes a big visualization effort, because we need to picture the three-dimensional molecule from this direction. Okay, so this hydrogen is this hydrogen. And basically this CH3 could be in different position. It could be on the right-hand side, which, for example, if we do the three-dimensional diagram, it would be that this CH3 comes towards us, while there will be a hydrogen going away from us. Yeah, and one hydrogen on the plane of the paper. Or we could have the other option that instead this CH3 group goes away from us, and instead we have a hydrogen coming towards us, because we always need to think about this tetrahedral arrangement of the carbon, this tetrahedral shape. Okay. And the most important thing to remember in this mechanism, which is E2, because we have one single step, and both the base and the haloalkane is involved in the rate determining step, so E2, it has always to be anti-periplanar. So to draw the Newman projection, we can always think about the relationship between the hydrogen that the base will attack, which is always this one, and then the bromine, which is the leaving group, that has to be always on the opposite side. So it's always this anti-staggered position. Okay. And so just staggered, not anti-staggered. So it's the staggered conformation. And then we can think about, okay, so the methyl group, or whatever group is attached to that first carbon, it can be in a different position, because notice how the back of the molecule, it stays, which is this one, it stays exactly the same. So it's that front one that will change conformation. So, and that's how we can draw the Newman projection. Then we need to think about, okay, but wait, but the Newman projection, which isomer is going to give us, E or Z? And I think the nice way to visualize it is that, well, we get rid of the HBr, because that's the mechanism. Elimination, it's the halogen that it's removed. But so what would the alkene looks like? And if we're able to visualize that this is gone and this is gone, and that this gives us a double bond, we can kind of see just the shape. I know it's a little bit weird, because it's just like this 2D paper is now a 3D, so we have to look kind of in this direction. But notice how we can see clearly that if we remove the groups that are removed and we put instead a double bond, look at the relative position of the other groups. They're on the same side. So this Newman projection would give, and here I'm just going to redraw it very easily, as well, these groups are, let me make this a bit bigger, these groups are on the same side. And the hydrogen are also on the same side. I'm just looking now from this direction. Okay. And what about the other one? Let's do the same type of visualization. We know we get rid of the HBr, so this is gone and this is gone. So instead here we have a double bond. And what's the relative position? Oh, now they are on opposite direction. And if we are able to visualize just that, yeah, which one is like the relative position of the groups, it makes it a lot easier to identify which one will be the Z and the E. So this one, same position, so it would be the Z. This opposite, it would be the E. And now we can go back to the Newman projection. So let me go back. And we can think about, okay, wait, so considering this, trying to look into the future of which one would be the E, which one would be the Z, we can think about which one would be the major, which one would be the minus. And here we just need to look at the position of the groups. Because when we have two big groups on the same side, here there is going to be some steric hindrance.
Okay.
So it's less favorable. While here the groups are on opposite side. So there is less hindrance between these groups, so it's going to be a lot more favorable, just favorable conformation, which means that this group overall would give us the major product, and the major product it's most likely, kind of all the time, to be the E, because the groups are far away from each other, so we know already that there won't be any hindrance. Okay.